to Baozi Training Lead Code Solution. If you want the best mock interview experience in North America, feel free to check us out at baozitraining.org. We are here to help you land your next big offer. And if you like the video, feel free to hit the like button and also help me subscribe. Okay, so today we're going to talk about, not a lead code solution. I should probably change the intro code, but anyways, it's going to be super quick. I have all the links here. So today we're going to talk about a very quick system design interview question, how to design a real-time chat system. For example, Facebook Messenger, WeChat, or WhatsApp. I think actually there's some open source thing we use. I think it's called Mattermost. So I'll put a link here as well. So there's a difference between you're going to do something versus you're actually going to design something, right? When you actually need to build something, prototype something super quick, you probably want to do some kind of research, especially on GitHub, some open source project that has lots of stars, for example, the Mattermost. And it's a very kind of like Slack look like type of open source system for real-time chatting. But if you're going to answer interview question like this, you probably want to follow these steps. So I summarize the methodology first is just keep in your mind whenever you're going to system design interviews, the acronym is called READ, motherfucker. It doesn't really sound very nice. It looks like a RTFM, but here's what the READ, motherfucker, really means. So it means requirement, estimation, architecture, details, miscellaneous, and the future. So the first thing you need to do, 6 steps, right, is you need to understand the requirement, do as many clarification as you need to, and also you can make some assumptions just to make your life easier. You don't want to kind of like design a super complicated thing first, because if you can design this nobody can design a WhatsApp in 60 minutes, right? So that's why there's a company worth $19 billion when Facebook bought it. Or you're just wasting time talking to the interviewers. So ask requirement, make it simple first, and also do a little bit of estimation just to show your analytical skills like QPS, storage size, network bandwidth, those kind of things. And then the third step is, if you don't know, just make assumptions. The interviewer probably doesn't know either. The third step is design a system architecture and layers. Always mention architectures and layers. For example, like this is the key design. I divide it into 3 layers. Presentation layer is more like a UI, and client service layer. This is the microservice architecture, where most of your business logic happens, and you can divide it into different components. We can drill down into any kind of components if we want to. And then the third layer is essentially the data storage layer. You have your cache, your main DB. You don't need to talk a specific solutions like MongoDB, Cassandra, MySQL. You can talk about it in general. And data warehouse, and also the more like the code storage like S3. The fourth step, the D stands for details. Drill down into details. That's kind of obvious, and also between those kind of services, you can talk, okay, what does connection service really do, right? For example, it maintains connection whenever a user comes online or offline. The client will send a message so that you know which client has a connection, those connection on which host, those kind of things. It's more like a lookup, but the chat server service maintains the actual connections. The fifth step is miscellaneous. This is really like similar to in real world life. When we talk about system designs, we talk about, okay, what kind of bottlenecks do you have? How do we handle peak traffic? For chatting app, it's very easy to have peak traffic, for example, earthquake or a soccer game. Failover, data center consistency, monitoring and alerting, security, threat, those kind of things, miscellaneous. And then the sixth step is, when you have time, you can talk about future work. How about supporting group chat, those kind of things. Those are some kind of key terms for these problems. You can talk about the WebSocket versus the normal HTTP layer. How do we maintain connection more efficiently? The idea is, because having you don't want to, for each of the users, right, they stay in the chat for a long time, you want to make sure the connection is reused, because establishing a connection under the IP TCP layer on the network and also the transportation layer is actually not trivial. So you want to utilize this. That's why here the chat service actually maintains some kind of like well, I wrap it into a service, so it's more like a hash map type of thing, right? For each of the conversation ID, you know which host in the chat server actually maintains this. So chat server will look into the connection service and then know, okay, which server in the chat service maintains connection list, and then we can forward the message to that server, and then that server can send those things. I should also draw how to kind of like a 3 bucket for image and video. That can happens in the future discussion in step 6. Yeah, data storage solution. We can talk about different things, right? So essentially, HBase, in memory, serialized to table, LSM tree is more like a log structure pending thing, which you don't change history, like Google Big Table. So this is actually very perfect for chat things. Cassandra SS tables can also do the same, or even Redis, you just maintain a queue for each of the service, and then you periodically sync the queue to a disk. So lots of things you can talk about here. Those are the last bullet point is send, deliver, and scene state. So it's pretty self-explanatory. So I actually, I give credit to all the existing resources on the internet. For example, the Grokking, the system design interviews. There's a PDF version you can feel free to download. Rick Reed, who already retired, I believe, is I think at least a staff engineer at Facebook/WhatsApp. He was the original one doing some perf work and then make sure and then achieve like at least 1 million connections, WebSocket connections per host commodity software. So you can check the video and the slide to see how he does it. It's mostly low level like FreeBSD and Erlang stuff. They actually contributed back to FreeBSD to improve some kind of the throughput to maintain those connections. Translate messages, okay, this is cool. And this is a good article on high scalability about how WhatsApp's skills. And then Tushar Roy, the guy, the engineering manager at Apple, explains from the interview perspective really well. So you can also check it out. The rest of them are pretty much not that helpful. There's a lot of YouTube videos explaining those, but I think, Rick Reed and also Tushar's things are very good. That'll be all. If you have any questions, feel free to leave any comments. Until then, I will see you guys next time. Oh, and I will also attach the Rick Reed's F8 video explaining about WhatsApp right along this video. So enjoy.
Good afternoon, everyone. Are you ready to hear how we do what we do at Facebook? Thank you. My name is Ryan Bergauer. I'm an engineering manager on the developer tools team at Facebook. And it's my pleasure to formally welcome you to day 2 of the engineering and open source track here at F8. If you missed day 1, don't worry about it. All the videos are available online at developers.facebook.com/videos. But our goal today is to give you as broad of an overview of Facebook engineering as we can fit into 3 hours, starting with talks from WhatsApp and Instagram around how they've used their engineering cultures to build apps at massive scale while still maintaining community. So, to help kick things off, help me welcome to the stage Rick from WhatsApp.
Well, hello, everyone. Thanks for coming. It's great to be here. I'm Rick Reed. Actually, let me start by saying, let me apologize in advance. I caught a cold over the weekend, and it decided that today was the perfect day to attack my voice. So please bear with me. I'm Rick Reed. I'm from the server engineering team at WhatsApp. My completely fictitious self-appointed title is the Deputy Prime Minister for Throughput. So my day job is scalability, and I'm here to tell you a story of scalability through the lens of my experience at WhatsApp. Now, I assume there may be a few users out there, but just in case, WhatsApp Messenger is a mobile messaging app that uses the data plan on your smartphone, allowing you to exchange text messages, share pictures, videos, audio files, documents, create group chats, make voice calls. Our mission at the company has always been to provide a simple, fast, reliable communications tool that would allow you to stay connected to all the people you care about, no matter where you or where they are in the world. And we are translated into 53 languages. Not too long ago, we announced that we had reached the amazing and frankly very humbling milestone of having more than 1 billion people using WhatsApp every month. Our users around the globe are sending over 42 billion messages every day, which if you average that out, that means almost 1 million messages every 2 seconds, which is just mind-boggling to me. Included in that is 1.6 billion pictures that are being shared every day and 250 million videos. So I began my career at a startup, and I remember those years being extremely interesting and rewarding and fun, but eventually I moved on and I spent the middle 2 decades of my career at larger tech companies, including Silicon Graphics and Yahoo. But I always had the dream that I could return to that startup environment, be part of a small team that was building something. And I was thrilled when the opportunity to join the team at WhatsApp came along. But from my first day, and really over the years, it seemed different to me. Obviously, it was different than what I was used to at the larger companies. It was different than I had remembered my startup experience in my first startup. But I think there are also some differences from what my expectation would be happens at our contemporaries in the startup world. So I'm going to talk about some of the keys, what I think are some of the keys to our success and how we've been able to scale. Now, this isn't meant to be necessarily a how-to. It's more of a we do. We do it this way because it works for our team and our mission. But hopefully you can derive some, derive some inspiration or maybe satisfy your personal curiosity about what makes WhatsApp tick. The 3 areas that I want to cover are fostering the right engineering culture, making some smart choices about the technology that underlies what you're doing, and finally, I'm going to talk about how we sort of face the challenge of operating at the scale that we're at. So you may ask, what does culture have to do with scaling? And I think, at least my experience, and many of us at WhatsApp feel the same way, that that culture really has everything to do with our ability to scale. Now, here's our team. This is WhatsApp. And there are really a few core principles behind pretty much everything we do. We try to keep things small. We try to keep things simple. And we have a single-minded focus on our mission and what we're trying to accomplish. So let's start with small. What does small mean? One of the other numbers that we released when we announced that we had reached our 1 billion user milestone was 57, which is about the number of engineers that are working at WhatsApp. And that's split about 50-50 between the server team and the engineers that are working on our client platforms. So our overall engineering organization is quite small, but within that, we try to keep our engineering teams, the individual teams, small as well. So from 1 to a few engineers, we work really hard to get just the right people into the right positions. The teams have a lot of autonomy, and they're really responsible for everything, from the design to the implementation, to the testing, the release, the deployment, the operations, the monitoring, responding to alerts, doing the troubleshooting, doing the capacity planning, really start to finish on the systems and the components that team is responsible for. So while we keep the engineering team small, and partly as a result of having an overall engineering organization that isn't very big, we also try very hard to keep our server footprint small. It's really as small as we can possibly get away with. Our goal going back a number of years was to try to have 1 million users for every server that we were operating. Now that's become a little bit more difficult over time as we've added features and our users have been generating more activity on a per user basis. But the bottom line is that we're trying to use a fewer number of larger, more capable servers And the reason we do that may seem somewhat obvious. Because we have a small team, it just makes it easier. And one of the primary reasons for that is that because we have a small number of systems, there are fewer things to break. Now, we don't run with a great deal of excess redundancy, so when inevitable failures do come along, we need to get those things fixed fast and get them back into production. So having a smaller number means that things are breaking less often, we're spending less time repairing those things, getting them back in, and just the overall overhead of operating those systems is lower for us. On the software side, we're also trying to limit the number of total systems and components that we're developing and that we're deploying and that we're supporting. That means that each team has a small number of systems that they're responsible for. So everything is getting constant attention. It's being refreshed because we're adding features, we're working on the scalability, we're working on the reliability. Whatever we need to be doing, we're in basically all of the code all of the time. And as a result, as a company, we're accumulating less tech debt in our systems. And that, again, makes it easier for us to manage with a small team. You don't find many projects or systems or components which are developed and then put into maintenance mode and eventually become orphans until something goes wrong. Again, because we're constantly refreshing the stuff all the time. So that's a few ways which we try to keep things small. What does it mean when we try to keep things simple? Well, it really starts with the app itself, of course. So, as I said, our mission is to provide a simple, fast, reliable communications tool without a lot of extra bells and whistles. You won't find many nice-to-haves in the app that aren't directly connected to that central mission of allowing people to communicate. But that really extends throughout everything that we do in engineering. We're big believers in just enough engineering. So just enough to meet whatever challenge it is, to implement whatever feature it is, to provide whatever scalability that we need where we're at, to provide the reliability, the security that we want. We don't overinvest in our systems or our components. We try to limit the number of software layers that we introduce. We try to limit the number of dependencies that we generate. So for most of our back-end systems on the server side, they're comprised of just a small amount of application code, perhaps a few library module dependencies, and that's really it. Now, when you look at decision making, so we're choosing among alternatives, different alternatives for an algorithm or the way that we're implementing something, the design of a new system, the design of a new feature. One of the key factors that, for us, that goes into that decision-making process is what is the simplest approach. That also means that we tend not to like I said, we tend not to overinvest in things, especially when it comes to tooling. Because we're a small team deploying a small set of software to a small number of servers, we don't invest a lot in automation except in the places that are absolutely necessary. So for instance, when we're pushing code for the server systems, we're generally just using makefiles, which sounds kind of prehistoric, but it actually works really well for us at our scale. But at the same time, we really like having the human in the loop there, somebody who's directly connected to the changes that are being pushed out onto our production systems. And I think it's been one of the reasons that we've had the kind of reliability and the success that we've been able to have. So why do we like simplicity? Well, it just makes things easier. It makes things easier to implement. It makes them easier to test. It makes them easier to deploy. It makes them easier to operate. They're easier to understand when they're working correctly and when they're not working correctly. We need to troubleshoot something. It makes it easier for new people to come in. It makes it easier for us to pitch in across the organization and work on various things. So it really makes things easier as a small team to be able to manage all the code that we're working on. So I'm going to give you a couple examples of what simple engineering looks to us, or just enough engineering. The first one is our transient multimedia storage. So this is the system where, for instance, pictures are stored between the time that they leave the sender's phone and they're received by the receiver's phone. So we went really simple with this. The client on the sender's phone is handed a URL that gets pointed directly at the storage server. that file is going to be stored upon. So that client is going to make a direct connection to a web server that's running on that storage server. It posts that file onto that server. It gets written into a file in a big hashed directory tree on the file system. We do need to store references to that file according to how many recipients there are in a database so that we can keep track of when everybody's received it and that we can remove it from the transient storage. On the flip side, when the receiver gets the message, that includes a URL, again, which points to the web server on that storage server where the file is located. The client on the receiver fetches that file. We remove the reference, and if all the references are gone for that particular picture, then that gets, excuse me, that gets removed from the file system, and that's really it. The second example I'm going to talk about is our offline system, or our transient message storage. So this is where messages are stored temporarily between the time that a sender sends a message to one or more recipients, and if the recipient's clients aren't currently connected to the WhatsApp servers, those messages need to go somewhere until the time that phone gets a notification and can connect and retrieve the messages, or if they're away from cellular or Wi-Fi coverage, come back into coverage. So again, super simple here. But in this case, the client has a connection to our front-end chat servers. That's their primary connection, where they're exchanging all the protocol messages. So that message is sent from the client to the chat server, which then determines whether those recipients are online, currently connected to WhatsApp, or if they're offline. And if they're offline, the messages get forwarded to the storage partition, which is basically a server dedicated for a particular set of users. On that storage server, on that offline server, again, the file system is the database. So each user has a file that corresponds to their mailbox. And as messages come in for them when they're offline, those messages are appended to that file. We call it a push operation. So we push the messages onto their mailbox as long as they're offline. And then when they come back online, the messages are popped. In other words, we read the file corresponding to that user, take the messages from there, forward them on to the client on the phone, and delete the file that's on the file system. There's really nothing more involved in what that system does. But of course, we need to have some redundancy in this because failures do occur, and we don't want to lose messages while they're in transit. So the model here, again, is very simple. So instead of having one storage server, one offline transient message store, we have two. We write in parallel to them. Those messages get appended to two parallel files in the file system that correspond to those users. And then when the user comes online, their client connects to the chat server, we pop from both. So we read twice, combine those two sets of messages, remove all the duplicates, forward them on to the recipient's phone, and then both files get deleted off the file system. This seems like way too simple. And these have been in production for years and years. And even at the time that we're implementing them, they seem too simple. But that is really what has worked for us. We've been able to scale both of these systems up many, 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 many times and still have the performance that we need. We have the scalability on being able to grow that system, and they've been incredibly reliable and easy to debug when problems do occur. Okay, so the final message I have about our culture is focus. We just celebrated our 7th birthday at WhatsApp, and every year we usually get a token gift that's inscribed with the word focus. A couple years ago, we got a magnet that had this on it: focus is the new F word. What does focus mean for us? Well, of course, it starts with the app. As I said, we're really dedicated to delivering just that core communications experience with our app. And so focus really is about just delivering a great user experience for what people expect in a communications tool like that. But that really extends to all the supporting systems and all the supporting tools that we have around that app. In addition, we try to remove all the distractions that we possibly can. So we really strive to be a no meeting culture. Now, that doesn't mean that we actually get away with having no meetings, because there are projects that cut across enough groups that we need to meet and exchange status, make decisions, but we try to minimize the number of meetings that we're having and keep them to a bare minimum time commitment. Instead, what we do is we really have sort of continuous conversations that are going on various messaging tools. Sometimes synchronous conversations, sometimes asynchronous, sometimes with email, but it really allows us to stay focused on what we're doing, and it actually contributes to a really quiet office. And now, this is one of the things that I first noticed when I started at WhatsApp, and there weren't very many people in the room, but boy, was it quiet. And it took some getting used to using my laptop to talk to Eugene and Jan, who were sitting next to me. But over the years, I've really come to appreciate the ability to sit at my desk, work on what I'm working at, but at the same time have an active conversation with whoever I need to in the office, whether it's a group or a person, without generating a lot of collateral noise and without having to book a room and figure things out at the whiteboard. We've also tried to remove as many external distractions as we can. We've been known as a company that sort of flies under the radar. We haven't sought attention. In fact, we've avoided as much attention as possible. We haven't put much energy into press, no energy into marketing. We don't do speaking engagements. If somebody asks, I'm not actually here right now. We really want to take all our energy and put it into delivering a great product and a great experience for our users using our product, so that the attention is really on how great WhatsApp, the messaging tool, is, and not WhatsApp, the company, is, even though the company is pretty great. We really want the focus to be on the app, and we want our time to be spent doing that. So I've described some about the WhatsApp mentality, but let's talk about some technology. So this is going to sound like common sense, but when choosing the elements of your technology stack, you really have to choose what's right for you. And in some cases, that means picking things that leverage your own strengths, your own experience. In other cases, it means leveraging the strengths of the things that you're picking. So I'm going to talk about 3 areas in terms of what we do on the server systems: our language, our operating system, and where we're hosted. Starting first with the language. So this is Agner Erlang. He was an early 20th century mathematician, and the namesake for the language that Ericsson developed in the early 80s, or excuse me, the late 80s, to run the control plane on their telephone switches. Now, Ericsson later open sourced Erlang in, I believe, the late 90s, but it's still developed and still used widely within the company. And it occurred to me when I was working on this talk that for many of the messages that our users are sending and receiving, they touch a lot of Erlang, because they may leave their phone, go through some Ericsson mobile operator equipment that's running Erlang. They'll go through our messaging system, which is Erlang-based, and possibly through some more Ericsson mobile operator equipment that's running Erlang. So Erlang end-to-end. Now, Erlang was designed for concurrency from the get-go. Is designed for distributed scaling, for low latency, soft real-time performance. Fault tolerance is a first-class feature of the language. And you really want that fault tolerance, of course. This was being designed to run the firmware on telephone equipment, which you want to be up all the time. So you would imagine that a lot of the features that are in that language would be very appropriate for any system that is sort of delivering this throughput model, but with high reliability, basically zero, nonstop performance. Now, we didn't have any previous experience with Erlang at WhatsApp, and the original decision to use Erlang was, at least in part, because the open source text chat server that formed the basis of the first WhatsApp server was written in Erlang. But over time, as that's been rewritten, as we've added more systems, Erlang has just proven again and again to be extremely well suited and perhaps uniquely well suited to what we're doing. So this is messaging at this global scale. We find that the development productivity on Erlang is very high. Now, it's a functional language, so it took a little getting used to, and for most people it takes a little getting used to, coming from a career of using imperative languages, so using recursion instead of loops, single assignment variables. The syntax is a little bit funky. It's derived from Prolog, but I've come to love it. But at the same time, Erlang is very concise. So our total code base is not very large because it's so easy to do a lot of things in a small amount of code. It has extensive library support that comes with what's called the Open Telecom platform, which is the encompassing platform for Erlang, including, now we don't make extensive use of the library because, as I said, we're trying to reduce our dependencies as much as possible. But we do make heavy use of some features such as the built-in database, which is called Amnesia with an M, which is either the worst or the best name for a piece of software that you want to remember things that I've heard of. But it works very well for us. Now, one of the key things that Erlang brings that has really been effective for us is the ability to hot swap code. So you can make changes to application code, and if you follow just a few simple rules, you can take that code and load it into the running application without really affecting anything. It doesn't break any connections. It doesn't kill any processes. Everything that was going on, as long as you do things right, just keeps going, but the new code is running instead of the old code. So this allows us to really easily deploy things. We have a really fast iteration cycle where we can get fixes out if there's a problem quickly. We can roll back things if we break something quickly. We can upgrade features. We have systems that have uptimes of over a year where they may get tens or hundreds or 1,000 code pushes. Really, you could rewrite an entire application from top to bottom and progressively load new code into it, all while it continues to run and be 100% available. And this has really worked well for us in being able to maintain the kind of uptime that we want our users to have and that they expect. Erlang also is great for performance in terms of what we're doing because it was built with concurrency from the get-go. It's a message passing model, shared nothing, which means that on our larger servers that we like to run. So we tend to have either 32 or 48 logical CPUs on our servers, and we're able to scale up the load on those systems pretty much all the way to full utilization of all the CPUs without running into a lot of contention, because the virtual machine is very well optimized to today's modern SMP hardware, and just the model and design of the language and the applications that run within it easily scale up without having to think a lot about how to make it scalable at that kind of level. Now, we did need to do a little bit of customization. There were a few patches that were needed in the early days because we are one of the largest Erlang systems. But it was pretty much ready to go with just a few minor tweaks. Now, our operating system is FreeBSD, which is also a somewhat unconventional choice today. Now, this was based on, in this case, we had deep previous experience. So Jan and Brian, our founders, and several of us on the WhatsApp server team were at Yahoo in the days when it was a FreeBSD only shop. And from that experience, we knew that it would be that it was particularly well suited to global scale network communications. It has a mature, high performance network stack. It's high scalability. One of my first tasks when I started at the company was to ensure that we were going to have the scalability that we needed without having to blow up our server count. So when I started, we were running a few 100,000 concurrent connections on each server, and our goal was to get to 1 million. On the Erlang side, it took a few code patches, mostly to the virtual machine, to eliminate a few contention points. But with respect to FreeBSD, it was really just tuning a few knobs, increasing the number of sockets that were available, reducing some buffer sizes, changing the size of some hash tables. But in short order, we reached that 1 million connections per server goal, and pretty shortly thereafter, we were able to get almost 3 million connections running per server. And that's not just a synthetic benchmark. We were actually running the production system like that with millions and millions of connections on each of the servers. In addition to the network scalability, its kernel is also great for the SMP scalability as well. So a couple of years ago, we were actually a little bit behind on our capacity planning, and the first that we noticed it was we started getting CPU overheat alerts. And when we went and looked at those servers, what was happening was they were running at like 98% CPU utilization. They were having cooling problems because they were running like that day and night. But our only indication that there was a problem was really that they were running too hot, because the scalability of both Erlang on top of FreeBSD without any contention meant that the throughput was just working as well as it possibly could at that completely saturated level, which is really rare to find. Lastly, we love the FreeBSD project and the community support for the OS. We like the model that the kernel development works from, which is basically progress with compatibility and stability at the top of mind. So we don't have to go through large-scale validation tests when we're moving between minor or even major versions of the OS. We just know that pretty much everything is going to work as we expect, even if the guts of something have been rewritten. So the software needs to run on some hardware, and we've been with SoftLayer almost since the beginning of the company. The original decision to use SoftLayer was really about two things: the availability of FreeBSD as a first-class operating system, and the ability to order and operate bare metal servers. Because, as I explained before, we're all about simplicity and trying to remove extra layers, so we wanted to run on the hardware, have direct control of the hardware. In addition, obviously, we need to have a great network. But in addition, we wanted to be able to have a simple network. So we wanted to have our clients connect directly to our servers without middle boxes or without extra tiers that we have to manage either from a capacity or a troubleshooting standpoint. So SoftLayer has that simple high-performance networking we need on the public side, but they also provide a segregated back-end private network, which is perfect for Erlang because Erlang is a distributed system. And the way that distribution works is through a mesh of TCP connections between all the nodes in the cluster. So the ability to put that distribution channel on the segregated backend allows us to get extra performance and reliability and security because those networks are segregated. We also tend to run really tailored hardware configs for each of the workloads that we're running. So if we have a large database, we'll stuff 768 gigs of RAM into those servers because for the most part, we keep all of our data in memory, both because it's fast and because, again, for simplicity's sake, we'd rather just have direct access to the data rather than worrying about caching tiers. On the other end of the spectrum, we'll have storage systems that have 6 or 8 or 12 or 24 SSDs, so a large amount of really high-speed, really reliable storage for the things that we need to store persistently. And then everything in the middle, we tailor the size of the RAM and the disk and the CPU so that we're keeping that server footprint as small as we can. Now, I mentioned that we don't run with lots of excess redundancy and we need to fix things fast. And SoftLayer works really well with us to get things repaired very quickly when they fail so that we can get those systems back into production. Now, of course, we joined Facebook family in 2014, and that just opened a wealth of world-class infrastructure for us to take advantage of. We've taken a measured approach to adopting that technology and really focused first on the thorniest scaling problems, which would include video. And this enabled us to scale up in ways that would have been a lot more difficult had we had to do it all by ourselves. So our engineering principles and our choices for technology have been there as we've scaled up. What are some of the challenges of operating our system at this scale? So if you look at our user count, so we have over 1 billion users using WhatsApp every month. The clients on their phones are connected to our systems at over 650,000 connections per second. And for the phones that are connected to the system, we're exchanging over 24 million protocol messages to and from those phones every second. So you can understand why simplicity is important to us, because we have a small amount of servers doing a large amount of work. And if there's a problem, if there's a bottleneck, if there's an issue we have to deal with, there's a lot that can go wrong every second because so much is flowing through the system. Now, it probably goes without saying that one of the things that makes scalability easy is ensuring that everything's horizontally scalable, so that as the workload grows, that you can scale up the hardware that's thrown at it easily without having to rewrite the software with just doing configuration changes and so on. We've ensured that we do everything with horizontal scalability in mind from day one. So there's never the case where we build a system to see if it works and then figure out how to scale it. Scalability is really, even going back to the beginning, we've built everything to be scalable and really, without a practical limit. So we don't build systems where we know, well, this will last us 2 years and then we'll figure it out. We start from day one and figure out, okay, what's the design that's going to allow us to just keep adding and adding and adding and adding as we grow. And that's really worked effectively for some of these systems that are 3, 4, 5 years old, and we've scaled up our user base and our messaging activity. But in order to know when we're going to scale something up, obviously we need visibility into what's actually going on. So one of the first tasks I took upon myself when I started at WhatsApp was to write a tool that was going to capture metrics. I didn't know Erlang, and I was a little frustrated that I couldn't be productive, but I did know Perl, and I did know we need this tool. So we were capturing over 100 metrics on every server, every second, looking at the system. The CPU utilization, virtual memory, disk, network, everything that we can find a stat for, we're logging it locally on that server. And then on a minute-by-minute basis, we're collecting even more stats, some of the ones that are more expensive to collect, and logging those remotely as well as locally. And then obviously we also capture aggregated statistics across the whole cluster at the application level. We're collecting thousands of those every minute. This gives us great visibility into what's going on, and we use this for everything. We use it for triggering alerts. We use it for troubleshooting, whether it's in real time, what's going wrong, or after the fact, what went wrong, or how did the system react. We also use it to do our capacity planning. So we're anticipating the growth over time. We're looking at how utilization of various parts of the systems are growing. We know roughly where the bottlenecks are, or where the limits are, and so as we get close to those limits, we know that we need to grow those systems, and of course that's where the horizontal scalability kicks in. But that handles the case of the expected growth in usage as we gain users and the users become more engaged. But what happens about when we have the unexpected? Now, in the messaging space, the unexpected is really about events that are experienced by a large number of people simultaneously. So something happens, and people want to, millions of people want to pick up their phone and they want to send a message to their family, to their friends, to their colleagues. And that means that within seconds, we can have millions of extra messages being dropped on the servers that need to get to where they're going, on top of the millions that we're already trying to deliver. So, of course, we start by making sure that we have headroom in our capacity. So even above our peak, we sort of anticipate how much extra space that we want to have, how much extra capacity we want to have to handle those events. But that doesn't always work. So what are a couple examples of things that drive these big spikes in usage? So one obvious example are earthquakes. So a lot of people feel an earthquake and they want to find out if their friends and family are safe. This is a plot of the messages being sent by our users in Chile during the September 2015 earthquake. So that initial shock was an 8.3 magnitude, and the shaking was 3 minutes long in the first shock. So you can see there's a little dip as the shaking starts, because people are obviously concerned, they're looking for cover, but the messaging rate picked up even before the shaking stopped, within 2 minutes, and eventually reached a level that was almost 4x normal for that country. The other interesting thing about this plot is you'll see several dips in it. Those are actually aftershocks. So as that messaging rate is climbing, there's one little dip there. That was a 6.4 magnitude aftershock. There are a few more dips there. There's a 6.1, there's a 5.6, a 5.1, a 6.1, and then that big dip is a 7.0 magnitude aftershock. So what's amazing to me is you can almost measure the size of the aftershock by looking at its effect on our messaging rates. This plot kind of looks like an earthquake. Is this a seismic graph? No, this is actually from the sporting world. So this is the 2014 World Cup match between Spain and the Netherlands, which was a rematch of the 2010 World Cup final. So it was hotly anticipated. You can probably count how many goals there were in this game. So Spain came out and got a penalty kick first, but then the Dutch came back with 5 unanswered goals. And as the game goes on, you can see increasing levels of excitement. Now this plot is zero-based, and it's our global messages received rate. So you can see on that final goal that our global messages receive rate was over 2x its normal value, just from people experiencing and wanting to share something about what's going on in that particular game. I have one more example here, which is from 2013. So here are 3 days in a row. One thing you'll notice here is that obviously we need to make sure that we have headroom where the peak is, not somewhere else, because often these things happen right at peak. That second day, the middle day there, that looks like a soccer game, and actually through the years we've sort of been able to identify what has happened based on what it looks like on the charts. That's an earthquake, that's a soccer game. This is a soccer game. This is Barcelona versus AC Milan. Again, this is global message receive rate. That third day, though, that doesn't really have the look of a soccer game. That was actually the election of Pope Francis. So the first spike there is when the white smoke was seen coming from the Sistine Chapel announcing that a decision had been reached, and then the bigger spike is when his name was actually announced. Now, we need to deal with these with providing that excess headroom in our capacity, but things don't always work out how we plan. And for those occasions, we make sure that the system is as loosely coupled as possible. And Erlang really helps with this. Since Erlang is a message passing system, there are message queues everywhere. Anything that's happening is a result of a message that's passing between two processes, some which might be on the same node, some which might be on different nodes. But in every case, there's a message queue that we can look at and see whether the system is keeping up with what's going on. So monitoring the size of the backlog on the message queues throughout the system are our primary mechanism for measuring the health of the system. If the queues are small or empty, we know that things are working well. If we start to get backlog somewhere, though, those are the things that we alert on. We can go specifically to those servers, to those systems, look at what things are being backlogged, what things are slowing down, and try to figure out what problem we need to address there. The message queues also give us a place that we can insert circuit breakers and relief valves in case there's traffic that we can, non-essential traffic, sort of at the protocol level, that we can drop and maintain the integrity of the overall system. We ensure that the messaging path, of course, is as free of obstacles as possible, so there's a clear path through there without a lot of places that latency can be added if things slow down. But the overall goal is to make sure that the system can stretch without breaking. So we can absorb incoming load, and it can be spread out through the system, through the message queuing, and through the various loose coupling mechanisms, and then gradually work through that. Maybe the messages are delayed by a few seconds, but we get them where they're going, and the system stays up. Now, one of the key things we do is try to learn from what's happened. So after an event, whether it's an unexpected world event, or it's some sort of issue that we had, we always go back and try to learn as much as we can about what happened and what we did to deal with it. So we have immediate postmortems within a day or two where we're looking at what the root causes were and ways that we can address those. And we try to get those fixes out immediately, really. Another aspect of the WhatsApp engineering culture is to really fix things right away. For most of our history, at least on the server side, we've pretty much operated without a bug tracking system. If we find something that's broken, we fix it and push it into production immediately, and we don't generate a big backlog of things that are broken and could potentially bite us and take our systems down. So when these events occur and we identify things, we get those fixes out there fast. And of course, the hot swap capability of Erlang helps us to do that because we don't have to go through a big release cycle to get that stuff into production. Now, equally important to identifying the root causes of what went on, we also look for places where there was contagion. So did a problem in one area or an overload in one area of the system cascade into other parts of the system? We use that to identify places that the system's overly coupled. And in the same way that we're addressing the root causes of a problem or the root bottleneck that contributed to the original problem, we also go through and fix all the places that we identified that didn't have enough loose coupling so that the problem cascaded from one place to another. Now, finally, when we're dealing with these problems and events, it's a firefight, right? And we have tools and dashboards and things that we're looking at to help us deal with the situation. But in the postmortem, we look back and see what we could improve. Are there metrics that we weren't collecting that we really should have known? Were there metrics that we were collecting but we weren't alerting on, so we weren't aware that they were in a danger zone? And then we look at our firefighting tools and discover whether there's things that would have made it easier for us to deal with that situation, given us greater visibility into what was actually going on, or made it easier for us to correct a configuration or to shunt some traffic or whatever it is. We try to make those, again, fixes to the tools as quickly as possible because we never know when the next event is going to come along. So in wrapping it up, I've talked about how we fostered a culture early on at WhatsApp that was really focused on giving our users an experience of a tool that was always on and always fast. We made key technology bets in the context of who we were and what we were trying to accomplish. And we built for scale from day one, but continuously improved what we were doing on a regular basis and as quickly as possible as we've learned from what we're doing as we've been scaling up the system. So I appreciate you coming. It looks like I have just a few minutes to take a couple questions. Thanks very much for coming. Yeah, there's microphones back there.
So you guys recently implemented end-to-end encryption in WhatsApp, and I was wondering if that made any significant changes to your architecture.
No, it didn't. Obviously, there was a major change to the protocols that we're using between the servers and the clients, and as well as between the clients themselves. Within the server architecture itself, though, it didn't make much difference because that part is mostly around transporting messages. We just changed the message types that were flowing through the system. But other than the protocol, the security protocols themselves, there wasn't a large change to the architecture of what we're doing.
Hi. Hey. Do you have any disaster recovery system in place for your server clusters? And I have a second question that you gave an example of the earthquake that happened in Chile. So do you have your server clusters based on geography so that disaster in one part of the world is not affecting the other parts of the world?
So as far as disaster recovery, yes, when I said we don't run with a lot of extra redundancy, we, of course, have enough that we can recover from those types of situations. We do base all our server resources in the US because we don't, as a messaging app, there's not a lot of a real-time component, so being close to the users isn't as important as it would be in certain apps. Now, of course, it is important for our voice calling feature, and we do leverage Facebook's Edge network, which is global, to take advantage of that. But beyond, but for just the core WhatsApp systems, those are all US based. In the back.
Hi. We work in a developing world, really big fans of WhatsApp. For our work, we've relied heavily on doing SMS-based interactions with our target audience for social impact. Now, WhatsApp has completely displaced that market and disrupted it and been very successful at that. And yesterday, we've heard Messenger released an API to do large-scale messaging. Is WhatsApp planning to open up an API for similar kind of API, well, interactions, specifically targeted at emerging markets?
Well, what we have announced earlier this year is that later this year, we're going to start experimenting with giving our users ways to interact with businesses and organizations that they choose to. I don't have any details to share on how that might look, but that's what we've announced so far in terms of opening up beyond just the core personal communications mission that we're currently focused on. Yeah, in the back.
So I appreciated your comment on focus, and I was curious if you had any suggestions for how to institute focus in a culture, an engineering culture.
That's an interesting question. For us, it was really top-down. So Jan especially, and Brian both, our founders, have kind of drilled it into us. Like I said, we get a yearly reminder that, we don't get a lot of swag at the company. So the things that we do get are usually either a milestone that we've reached, or they say focus on it. Beyond that, it's hard to say how you come in after the fact and do that, because that focused mentality really grew up with the company. Like I said, when it was still very small, and we were still operating at the way that it was when it was just a handful of people, and I wouldn't say that there was anything special that we did to do that, other than that culture just grew organically, basically as a result of kind of the attitudes of the founders. I know that's not a great answer, but that's kind of how that's the one I have. That's what worked for us. Yeah.
What do you think about Elixir, this new language in top of Erlang? I don't know if you have heard of it.
I've heard of it. I don't know a lot about it, to tell you the truth. I haven't. We typically go to the Erlang conference in San Francisco, and there's obviously a lot of buzz around Elixir, but I honestly don't know that much about it or how it would, how it might pertain to what we're doing. We've been very happy with Erlang itself, and haven't really been looking for a reason to bring in anything else. So for that reason, I haven't really kept in tune with what's going on there.
Thank you.
All right. Thanks very much. Enjoy the rest of your day.